I'll just start all over again because there was a long pause now. So I just stopped that recording and I started again. So children who missed today's class will be using the recording. So I'll just start over. So circular park, center O, 3 friends R, S, M on the boundary. This is the distance between R and S. This is the distance between S and M, given to us 6 meters. We need to find the distance between R and M. So we need to find Rm. Rm is what we have to find. Radius of the circular path given. In the answer here, I've joined OM, but I told you that we can also join OS, OR. OR represents radius, OS radius, OM also radius. Anything just to, show the radius 5, which is given 5 meters. You can also join this one like this, so 5 meters. All right, so this is what is, this information is given to us, and with this we need to find the length of the line segment Rn. All right, so first I'll just tell you how the entire proof goes. So first we need to join SO and show that triangle RSO is congruent to triangle MSO. That is step 1. Show that triangle RSO is congruent to triangle MSO. Okay. So in these two triangles, RS is equal to MS given. RS of this triangle is equal to MS of this triangle, 6 meters given. RO of this triangle is equal to MO of this triangle, radius. RO radius, MO radius. So 5 meters. Radius are radii of the same circle, they're equal. So RO is equal to MO. And then SO is the common side. SO is the side common to both the triangles. So by SSS congruence criterion, these two triangles are congruent to each other. So CPCT, you will have angle 1 is equal to angle 2. CPCT, angle 1 is equal to angle 2. It is for this reason we want this information. That's why we show that the triangles are congruent. All right. Okay. So this is the first step. Show the triangle RSO is congruent to triangle MSO using the SSS congruence criterion. The 3 sides of one triangle are equal to the respective 3 sides of the other triangle. Okay, then CPCT angle 1 is equal to angle 2. Now, this information is useful to show that, let me just mark this point as N. Now, this, sorry, so this information we need to show that triangle RSN is congruent to triangle MSN. This is the next thing we have to do, step 2. We need to show that triangle RSN is congruent to MSN. So how is this? RS is equal to MS given. Angle 1 is equal to angle 2 proved. SN is equal to SN common side. So by SAS congruence criterion, these two triangles are congruent. Triangle RSN is congruent to triangle MSN by SAS congruence criterion. We'll see the equalities again. You see the equalities again because RS is equal to MS given 6 meters. Angle 1 is equal to angle 2 proved. Then SN is equal to SN common side. So you can see that angle 1 and angle 2 are the included angles. So SAS rule, the triangles are congruent. So CPCT, we have angle 3 is equal to angle 4. CPCT, we have angle 3 is equal to angle 4, CPCT. But angle 3 plus angle 4 is equal to 180. So angle 4 plus angle 4, because 3 is equal to 4, no? So 4 plus 4 is 180. Twice of angle 4 is 1. So we proved that 4 is 90 degrees. So if this is 90 degrees, ON is a perpendicular from the center to the chord. So it bisects the chord. So that way NM is equal to NR, or you can also say NM is equal to NR CPCT. Because the triangles are congruent, no? In step 2, we have proved that the triangles are congruent. So NM is equal to NR CPCT. From step 2, we write two results by CPCT. One is angle 3 is equal to angle 4. And we use that further to show that angle 4 is 90 degrees. And then the other result we write is and the other result we write is NM is equal to NR CPCT. Now coming to the, the main part of the answer. Now the idea is, if you look at the triangle, SOM, we know all the three sides of this triangle. See, you can take up the triangle SOM, or you can take up SOR also. Anything. You can take up SOM or SOR. Now, once we finish the, we come to the end of the answer, we'll understand why. So now you can take up the triangle SOM or SOR. Find the area of this triangle using Heron's formula. Because SO is a radius 5 meters. OM, radius 5 meters. SM, given 6 meters. So we know all the three sides of this triangle SOM. So let's find the area using Heron's formula. Now after that, so quickly let's find the semi-perimeters. 5 plus 5, 10, 16. 16 by 2, 8. Then square root of 8 into 8 minus 5, 3. 8 minus 5, 3. And then 2. So it will be 3 and 16. So 3 for the 12. 12 is the area, children. The area of this triangle is 12. Area of triangle SOM is equal to 12 meters square using Heron's formula. Now, you see that MN is an altitude of this triangle. MN, because this is 90, no, we proved this is 90. This one is 90. So clearly MN is an altitude from the vertex M to the side OS. That's why we proved 90. That's why we proved 4 is 90. Now in the same triangle, I'm saying SOM, MN is an altitude from the vertex M to the opposite side SO. This is the triangle. This is the triangle SOM. This is 6. This is the radius 5. This is also the radius 5. And we have this one. This is that N. Now the area of this triangle is 12 meters square. Now MN is an altitude from the vertex M to the opposite side SO. Now let's find the length of the line segment or the altitude MN. Once you find MN, double it, because we know yeah. So once you find MN, we know that MN is equal to RM, CPCT. Okay, we know that MN is equal to NR. So once you find MN, double it to find RM. and that is the distance between R and M. That's what we had to find, the distance between R and M. So Mn is an altitude of the triangle, right? So area of triangle SOM is equal to 12. We found using Heron's formula. Half into base SO into altitude Mn is equal to 12. We already found the area of this triangle using Heron's formula. Okay, it's 12. Now, the same answer you should get now if you use half base into height for the same triangle. If you try to find the area using the formula half base into height, you should get the same answer. So half into, let's take the side SO as the base, because we know the corresponding altitude is Mn. So half into side SO into the corresponding altitude Mn is equal to 12. So half into SO is a radius, children. So 5 into Mn is equal to 12. So Mn is equal to 12. 5 by 2 will become 2 by 5 on the other side. So 24 by 5. 12 2s are 24. 24 by 5. So 5 4s are 20.8. 4.8. 4.8 meters. 4.8 meters. So the distance between R and M is 2 into 4.8, which is 9.8, 9.6 meters. 9.6 meters. We'll quickly see this again. So step 1 is to show that triangle RSO. RSO is congruent to triangle MSO. SSS. Because RS is equal to MS 6 meters. SO is equal to SO common side. RO is equal to MO radius. RO radius, MO also radius. So SSS rule, the triangles are congruent, and we want this result. CPCT, angle 1 is equal to angle 2. Angle 1 is equal to angle 2. Then prove that triangle, let's mark this point N. Triangle RSN is congruent to triangle MSN. So this happens by SAS. SAS, because this side is equal to this side. Included angles. Okay, this side is equal to this side. This is the common side. So angle 1 and angle 2 are the included angles, and they're equal because here CPCT. So like this, the two triangles are congruent. CPCT, we have angle 3 is equal to angle 4. Angle 3 is equal to angle 4. But 3 plus 4 is 180 because linear pair. So 4 is equal to 90. Angle 4 is equal to 90. Yeah. So angle 4 is equal to 90. And also CPCT, Rn is equal to Mn. Rn is equal to Mn CPCT. So now the idea is we'll find the length of the line segment Mn. Mn we'll find, and then we'll double that to find Rm. So how to find Mn? Mn is an altitude. Mn is an altitude of the triangle MOS. Okay, so Mn is an altitude of the triangle MOS. So what we're going to do is we're going to find the area of this triangle MOS We're going to find the area of this triangle MOS using Heron's formula because we know the lengths of all the three sides. Okay, SO is the radius 5 meters, MO radius 5 meters, MS it's given 6 meters. So we know the lengths of all the three sides of this triangle. So we find the area using Heron's formula and we found that to be 12 meters square. So half into base. OS is a side. OS is a side of this triangle. So we take that as a base into the corresponding altitude, MN. Because the altitude MN lands on this side OS. So if you take this as the base, this is the corresponding altitude. Is equal to 12. So when you work this, because OS is 5, when you work this, you find MN is equal. OS is 5 is given. So MN you get 4.8. So MN is 4.8. MR is 2 into 4.8, which is 9.6. So that's about the fifth one. 4 we finished the other day. Now 3. If two equal chords of a circle intersect within the circle, if two equal chords of a circle, see that equal chords, if two equal chords of a circle intersect within the circle, okay. So let us say that AB and CD are two equal chords. And they intersect within the circle at this point. We'll just call that E. Okay. If two equal chords of a circle intersect within the circle, prove that the line joining the point of intersection to the center. So this is the center. This is the point of intersection. And this is the line. This is the line joining the this is the line joining the point of intersection and the center. Line. So you can just leave, you can even produce it like this. Or you can stop here. Anything is fine. You can stop it here. Or you can just show because it's given a line, no? So you can extend it outside the circle and use arrows. That's fine. You can also stop it like here. You can also just leave it like this. Yeah. So you can say this is the line segment. Okay. So it's a part of a line. So this line, what does it connect? It connects the point of intersection and the center. So prove that the line joining the point of intersection to the center makes equal angles with the chords. So see here, this is the line and this is one chord. This is the line and this is one of the chords. So this is the angle between the line and the chord. This is the other chord. This is the other chord. Yeah. So this is the other chord and this is the angle between the line and the chord. So we need to prove that this angle is equal to this angle. We need to prove that this angle is equal to this angle. Circle, two chords intersect within the circle and the two chords are equal. Chord AB is equal to chord CD. So the point of intersection is E and the center of the circle O. This is the line joining the point of intersection and the center. Now this is the angle between this line and this chord. And this is the angle between this line and this chord. we need to prove that angle 1 is equal to angle 2. Prove that the line joining the point of intersection, this is the point of intersection, E is the point of intersection. The line join so this is the line joining the point of intersection and the center. You must prove that this line makes equal angles with the chord, equal angles. So you should prove that angle 1 is equal to angle 2. Very simple proof, because congruency, CPCT, you will get angle 1 is equal to angle 2. So for that, we need to have triangles. And I mentioned this in the last class that in this chapter, in circles, the default construction is drawing the perpendicular from the center to the chord. Remember that. Construction, drawing perpendiculars from the center. All right. So we draw perpendiculars from the center to the chord. That's a default construction. Drawing a perpendicular from the center to the chord is the default construction. So, all right. Okay, so now that also helps us to get two triangles. Now, you should get all the theorems in your mind. We know that the perpendicular from the center to the chord bisects the chord. The perpendicular from the center to the chord bisects the chord. That's one thing. And then equal chords are equidistant from the center. Now we are trying to recall the theorems, like based on the situation we have here. Since we have drawn perpendiculars from the center to the chord, so we know that it bisects the chord. That's one thing. If needed, we'll use it. And the other thing is equal chords are equidistant from the center. Because chord AB is equal to chord CD, OM is the distance of chord AB from the center. ON is the distance of chord CD from the center. And OM is equal to ON because AB is equal to CD. If two chords are equal in length, then their distances from the center will also be equal. And distance is always perpendicular distance. And that's the construction. Draw OM perpendicular to AB. Draw ON perpendicular to CD is the construction. And because AB is equal to CD, the distance of chord AB from the center is OM. And the distance of the chord CD from the center is ON. Since AB is equal to CD, by the theorem, OM is equal to ON. Now, in the two triangles, this side is equal to this side, 90 degrees, common hypotenuse. Yeah, you can see it now. This is construction, so 90 degrees. R, right angle. This is a common hypotenuse. This is the common hypotenuse. Here, right angle by construction in the two triangles. Then common hypotenuse. And sum of the side, RHS. OM is equal to ON. So by RHS congruence criterion, the two triangles are congruent. CPCT, angle 1 is equal to angle 2. Got that, children?
Yes, ma'am.
Yeah. Don't write down now. Just go through. Okay. If two equal chords of a circle intersect within the circle, prove that the line segments of one chord are equal to the corresponding line segments of the other chord. So again, same situation. If two equal chords of a circle, so AB and CD are two equal chords, and they intersect within the circle, say at E. Now, because the two chords intersect, the chords are divided into line segments. Like if you look at the chord AB, it is divided into the line segments AE and EB. And when you look at the chord CD, it's divided into two line segments, CE and ED. So you must prove that the corresponding segments are equal. That is, you must prove that the segment CE of the chord CD is equal to the segment BE of the chord AB. We need to prove that the corresponding segments are equal. See, AB is one line, is a chord is one line segment. CD is one chord, one line segment. But since they intersect, they are further segmented. So AB has two parts, AE and BE. CD has two parts, CE and DE. Now, the question is, we need to prove that the corresponding segments are equal. So this segment of CD corresponds to this segment of AB. This segment of AB corresponds to this segment of CD. Is the statement understood, children? Not understood? Please respond. Do we understand? Okay, so this is what we'll have to prove. Okay, so what's the default construction? I'll show you the answer slide. You go through. I want. Go through and then I'll ask you questions. Then you should be able to answer. Yeah. Now tell me. Yeah, what's the construction? Okay. Draw OM perpendicular to AB. Draw ON perpendicular to CD. Dropping perpendiculars from the center to the chords is the default construction. From the center, draw perpendiculars to the two chords AB and CD. So OM perpendicular to AB, construction. ON perpendicular to CD, construction. Then also we need to join because we want two triangles. We want two triangles, na? So we'll join this, join EO. So now we have this triangle and this triangle that show that these two triangles are congruent. So you see right angle, common hypotenuse, and ON is equal to OM because the two chords are equal. It's given two equal chords. So since the two chords are equal, their perpendicular distances from the center will also be equal. So in the two triangles, so we have taken the triangles EON and EOM. In these two triangles, right angle is by construction. EO is the common hypotenuse. And some other side, ON is equal to OM. Because the chords are equal, their distances from the center are also equal. So like this, by RHS rule, the two triangles are congruent. So CPCT, here we don't want to say some angle is equal to some angle. No, because we need to prove that some segments are equal. Segments are equal. So you can clearly see that EN is equal to EM. This may be useful. You can get few other results by CPCT, but they'll not help you because we need to prove some segments are equal. So this is the only information that will be helpful. Right? So, so this is the only information that can be useful. EM is equal to EN. The other results by CPCT will not help you to, we have to prove that we'll have to prove that AE of the chord AB is equal to DE of the chord CD. And we also have to prove that BE of the chord AB is equal to CE of the chord CD. We have to get these results. So for this, in all probability, only this information will be useful. EN is equal to EM. EN is equal to EM, CPCT. EN is equal to EM, CPCT. This only can be useful. Now, see. We have to show that BE is equal to CE, right? Look at this carefully. BE is equal to CE. Now, what is BE made up of? BE is made up of BM and ME. BM and ME. BE is BM and ME. And what is CE made up of? CN and NE. Now, we have proved that these two are equal. CPCT. And we can prove that these two are equal. BM is equal to CN. BM is equal to CN. We can prove. Because the two chords are equal, right? The chords are equal. So their halves also will be equal. How do we know their halves? Because the perpendicular from the because we know that the perpendicular from the center to the chord bisects the chord. OM is a perpendicular, is the perpendicular from the center to the chord. So it bisects the chord. So M is the midpoint of AB. In the same way, N is the midpoint of CD. So that means because AB is equal to CD, their halves, BM is equal to CN. The perpendicular from the center to a chord bisects the chord. OM is perpendicular to AB. Therefore, it bisects AB, which means M, not E. OM is the perpendicular, right? So M is the midpoint of AB. ON, perpendicular from the center to the chord. So it bisects the chord. So N is the midpoint of CD. So since the chords are equal, their halves also will be equal. Since the chords are equal, their halves also will be equal. So AB is equal to CD. Half AB is equal to half CD. Half of AB is BM equals half of CD, which is CN. Now, BM plus ME, no? ME and CN plus NE. Yeah, we know that ME is equal to NE. We proved CPCT. Write that below this. Now add these two. BM plus ME is BE is equal to CN plus NE is CE. So hence prove BE is equal to CE. Now, we know that the chords are equal. AB is equal to CD. From that, subtract this result. BE is equal to CE. So what is AB minus BE? AE. And what is CD minus CE? DE. This is the other result. So it's simple. Just show that the triangles are congruent. So given that chord AB is equal to chord CD, they intersect inside the circle at E. O is the center of the circle. Draw perpendiculars from the center to the chords. And also join EO to get two triangles. Show that these two triangles are congruent. So RHS, they're congruent. This side is equal to this side because equal chords are equal. See, you should not struggle to get the third information because two are direct, 90 degrees and this common hypotenuse. Now that other information, RHS. So remember that when two chords are equal, their distances from the center is also equal. So OM is equal to ON, that becomes S. So RHS rule, the triangles are congruent. CPCT, ME is equal to NE. This one is equal to this one, CPCT. ME is equal to NE. Now you must write AB is equal to CD, given. Half of AB is equal to half of CD. Now, to write half AB equals half CD, you need to know the midpoints. Only then you can write half. You can take half, meaning you can find halves of equals only if you know their midpoints. And here, yes, we know the midpoints of A, B, and C, D by the theorem that the perpendicular from the center to the chord bisects the chord. So M and N are the midpoints of the chords. So half of AB, you can write AN or NB. You can write AN or NB. N is the midpoint, no? So you write NB, that is BN, is equal to half of CD, right? CM. And to this result, you add that CPCT result. CPCT, we proved that this side is equal to this side, no? Add that. So to BN, add NE. And to CM, add ME. So BN plus NE is BE. CM plus ME is CE. Now from the whole, chords A, B, and C, D, if you subtract these results, BE, if you subtract this, you will get AE is equal to CD and CE is D. Okay. 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 So if two intersecting chords of a circle, see, look at that, not two equal chords. If two intersecting chords of a circle make equal angles with the diameter passing through their point of intersection, prove that the chords are equal. So it's the converse of what we saw in the exercise. It's the converse of this one. The second or the third question in the exercise. This one. If two equal chords of a circle, no, not this one, sorry. Yeah, this one. Converse of this one. If here it is two equal chords, they intersect within the circle, prove that the line joining the point of intersection to the circle to the center makes equal angles with the chords. Here the chords are given to be equal. We have to prove that they make equal angles. In the example, it's given that the chords make equal angles with the line joining the center and the point of intersection. It's given that the angles are equal. You need to prove that the chords are equal there. See, the two things are chords and the angles. Chords and the angles. The two chords and the angles made by these two chords with the line segment joining or passing through their point of intersection at the center. Here the chords are equal. You need to prove that the angles are equal. In the example here, the angles are equal. You need to prove that the chords are equal. If two intersecting chords of a circle make equal angles, they make equal angles with the diameter passing through their point of intersection. You need to prove that the chords are equal. So this is the point of intersection of the two chords. A, B, and C, D are two chords. We'll have to prove that they're equal. They intersect here at E. This is the diameter passing through their point of intersection. This is the diameter and the diameter passes through the point of intersection E. It is given that this angle is equal to this angle. It's given angle 1 is equal to angle 2. Angle 1 is the angle between the chord and the diameter. Chord CD and the diameter. And angle and angle 2 is the angle between the chord AB and the diameter. It's given that these angles are equal. Angle 1 is equal to angle 2 is given. You need to prove that AB is equal to CD. You need to prove that AB is equal to CD. Okay. So construction, drop perpendiculars from the center to the chords. Now here, ON is not equal to OM because the chords are not given to be equal. We have to prove they're equal. So here, since AB and CD are simply two chords, they are not given to be equal chords. We have to prove they're equal. So we don't have this information that, or we cannot conclude that OM is equal to ON. No. Because AB is not given to be equal. We have to prove it's equal. So we can't use this information. OM is equal to ON. As of now, OM is not equal to ON because the chords are not equal. So construction is perpendicular from the center to the chords. So we have 90 degrees. 90 we have. I'm saying like you can't use this. These two are equal. Okay. So 90 degrees on the two triangles. Then this angle is equal to this angle. That is, this angle 1 is equal to angle 2 and common side. AAS. Triangles are congruent. CPCT, OM is equal to ON. So we proved that OM is equal to ON. That is, the distance of the two chords from the centers are equal. Then the chords are equal. OM is equal to ON means the perpendicular distance of the two chords from the center are equal. So if the distance of two chords from the center are equal, then the chords are equal. Chords that are equidistant from the center are equal. Chords that are equidistant from the center are equal. So since OM is equal to ON, OM is the distance of AB from the center. ON is the distance of CD from the center. Since OM is equal to ON, AB is equal to CD. Since the distance of the two chords from the center are equal, the chords are equal. If chords are equal, if AB is equal to CD, then OM is equal to ON. If OM is equal to ON, then AB is equal to CD. So we just have to prove that the triangles are congruent. Result by CPCT, OM is equal to ON. And the theorem, chords that are equidistant from the center are equal. Therefore, AB is equal to CD. You can just go through this. I'll just come back. Yeah, go through this one, children. With this, we finish the example before this exercise and all the 6 questions from this exercise 10.4. So now, if we have to draw a pair of circles which have no point in common, 2 circles which have
Ma'am,
no point. Yes.
I have a doubt.
Uh, can I just finish explaining and then you can ask me, Anirudh? Is it regarding this
Okay,
answer?
ma'am. Ma'am.
Yeah. I'll just finish. Yes.
Okay, ma'am.
Yeah. So if we have to draw 2 circles which have no point in common. So 2 circles which have no point in common. I have the introduction PPT. I'll share that with you. I'll just tell you now. I'll share the PPT which you can use later. Now 2 circles that have 1 point in common. 2 circles that have 1 point in common. Two circles that have 1 point in common. So these are called touching circles. These are called touching circles. So touching circles have exactly 1 point in common. So touching circles, one circle can lie inside the other, or they can be like this. They can touch each other, one lying internally or like this. The circles that have no point in common. Circles that have no point in common. Circles that have exactly one point in common are touching circles. They can touch internally or externally like this. Only one point in common. Intersecting circles have 2 points in common. Intersecting circles have 2 points in common. You cannot draw two circles having more than 2 points in common. Like you cannot draw two circles that have 3 points in common. So when you take two circles at a time, either they'll have no point in common, or they'll have exactly 1 point in common, or a maximum of 2 points in common, not more than that. So when we take two circles, we can draw two circles in such a way that they have no point in common, or they have exactly 1 point in common. In the case of touching circles, they can touch, two circles can touch internally or externally. So touching circles will have only 1 point in common. Intersecting circles will have 2 points in common. Touching circles are different from intersecting circles. Intersecting circles will have 2 points in common. So here you can see intersecting circles, they have 2 points in common. These are the 2 points, A and B are the points of intersection. So these are the only 2 points that are common to both the circles. Circle meaning on the circumference. On the circumference, only on the circumference, not the circular region. On the circumference, we have only A and B in common. The two circles have many points on their circumferences, but these 2 points A and B are common to the two circles. So that's where the two circles intersect. Now, when you join the points of intersection, you get a chord which is common to both the circles. You can see that AB is a chord that lies in both the circles. When you draw two intersecting circles, and when you join the points of intersection, that line segment is the chord which is common to both the circles. You can see that AB lies in both the circles. So AB is a chord to the first circle, AB is a chord to the second circle, so AB is a common chord to the two circles. Now consider the centers of the circles, O and O dash. When you join the centers, this is always the perpendicular bisector of the common chord. That's a theorem. That's a theorem. The line segment joining the centers of two intersecting circles is the perpendicular bisector of the common chord. Let's see this situation again. Two circles, two intersecting circles. A and B are the points of intersection. Join the points of intersection. AB is a common chord to the two circles. O, center of the first circle. O dash, center of the second circle. Join the centers. Now, O dash is the perpendicular bisector, of AB. O dash is the perpendicular bisector of AB. That means O dash and AB will make 90 degrees. O dash and AB will make 90 degrees. And also AB is bisected, not O dash. O dash is the perpendicular bisector of AB. AB is bisected. O dash need not be bisected. The line segment O dash need not be bisected. According to the theorem, the common chord is bisected. That means This one is the midpoint of the chord AB. Two circles intersect at points A and B. AB is the common chord. O dash is the line segment joining the centers of the two circles. The line segment joining the centers of the two intersecting circles is the perpendicular bisector of the common chord, here AB. This is a theorem. We have the proof. We'll see the proof later. Okay. So here what we do, center of one circle, center of the other circle. Center, center, because 5, 3, this will be 3.5, 2.5. Yeah, okay. Whatever, the way you draw the diagram is not going to affect the answer. It's the properties which we use that matters. So I've marked the centers of the two circles. This is the common chord, AB. AB is the common chord. This is the line segment joining the centers. Okay, this is the line segment joining the centers. So we know that it makes 90 degrees, and also this is the midpoint. M is the midpoint of AB. Now, this is the radius. Radius, no? This is radius. The radius of the first circle is the radius of the second circle. This one is, say, O dash, this is O. M is here, children. Center, this is O dash. This is M. Center O. Yes. So we know that the radius of the first circle is 5 centimeters. Second circle, OA is 5. O dash A is 3. And O dash is 4, because it's given. The distance between their centers is 4 centimeters. 4 centimeters, sorry, okay. In triangle O dash A, we know the lengths of all the three sides. O dash is the distance between the centers. So 4 centimeters. O dash A is the radius of the second circle, 3. OA is the radius of the first circle, 5. So we know the lengths of all the three sides of this triangle. So you can find its area using Heron's formula. Now let's find, oh, I wrote M, is it? I thought that I had written meter. Sorry. This M, I thought I wrote meter and I changed it to centimeter. This is M. Okay, so we find the so we find the area of the triangle O dash using Heron's formula, because we know the length of all the three sides. Now, after finding the area of the triangle, I'll just copy. Oh, it's a right triangle, no? So 6, yeah. Okay, so the area we find is 6 using Heron's formula, 6 centimeters squared. So the area of the same triangle can be found using the formula half base into height. So half into base O dash into height AM. You can see that if you take O dash as the base, the height is AM, because from the vertex A, AM is an altitude on O dash. So if you take O dash as the base, AM is the altitude, is equal to 6. So half into O dash is 4 into AM is equal to 6. So AM is equal to 6 by 2, 3. If AM is 3, AB is 6 because M is the midpoint, right? By the theorem, M is the midpoint. So if AM is 3, AB is 6. So the length of the common chord is 6. The length of the common chord is 6. We'll see it again. Circles, intersecting circles. A and B points of intersection. O center of the first circle, O dash center of the second circle. Common chord. Actually, this O dash will lie on the common chord that you can make out by construction. Now, the diagram is a rough diagram. So for these values, actually O dash will lie on AB. Okay. So AB is the common chord. AB is the common chord. O dash is the line segment joining the centers. O and O dash are the centers. And O dash is the line segment joining the centers or the distance between the centers, 4. OA, radius of the first circle, 5. O dash A, radius of the second circle, 3. So clearly, we know the lengths of all the sides of the triangle O dash OA. Find the area of this triangle using Heron's formula, and that is 6 centimeters squared. Now, by the theorem, the line segment joining the centers, that is OO dash, is the perpendicular bisector of the common chord AB. That means OO dash and AB, they meet at right angles. The line segment joining the centers OO dash and the common chord AB, they meet at right angles. And also, if you mark this as M is the midpoint of AB. That is OO dash bisects AB. M is the midpoint of AB. So we found the area of this triangle using Heron's formula. Now, area of the same triangle can be found using the formula half base into height. Half into base OO dash into height AM will give you the same area 6. So half into the base OO dash is 4. The line segment joining the centers. The distance between the centers is 4. Into AM we don't know is equal to 6. If you take this as the base, this is the corresponding altitude. So you get AM is equal to 3. If AM is 3, because M is the midpoint of AB is equal to 3 into 2, 6 centimeters. Yes, Aniruddhan?
Yes, ma'am.
Yeah. If you still have a question, you can ask me.
No, ma'am.
Okay. The diagram is a rough diagram, children. Don't worry that you have to draw it like this. It's a rough diagram. However you draw, see this, it should be meaningful, the diagram. The circles must be intersecting, all that, whatever we discussed. The diagram should suit the situation, that's all. But it's okay how it looks like. You will still get the same answer. So that's what we've done here. See, I first mentioned the theorem. O dash is the perpendicular bisector of the common chord AB. So OMA, this is 90 degrees. O dash, that is this one. O dash MA. O dash MA, this one. It's enough if you write OMA is 90. OMA is 90. Then we find the area of the triangle. Heron's formula. Then the same triangle using half base into height. So we find AM and double AM is AB. Children use the emoji. Raise your hand. Abhishek, Bhavishya, Haripranav, Ritsa, Prenu, Aragamai, Aniruddhan, Sabarna, Sadhna, Kamalika, Niveda, Sahana, Hariharan, Srivatsan, you're there? Okay. All right. This is the last exercise, 10.5 in circles. Those who've learned this chapter at school, in circles, nothing has been deleted, right? Am I right? Ten point five has been done in school, right?
Yes, ma'am. Yes, ma'am.
Yeah. Okay. Okay. So this is exercise 10.5. I'm coming from behind. This is the, I think, yeah. Correct. Yeah. So prove that a cyclic parallelogram is a rectangle. Prove that a cyclic parallelogram is a rectangle. Remember that the diagram should suit the final result. The final result is a rectangle. So when you draw the cyclic parallelogram, the parallelogram should already be a rectangle, because only then when you say therefore ABCD is a rectangle, when you look back at the figure, it looks like a rectangle. See, you cannot draw something like this and say that therefore ABCD is a rectangle, right? So always draw so that the diagram suits the result which is to be proved. And hence we draw ABCD in the shape of a rectangle, because that's what we love to prove. And it's cyclic. It's cyclic because it's given as a cyclic parallelogram. So you can see A, B, C, and D lie on the circumference of a circle. And ABCD as of now is only a parallelogram. ABCD is cyclic and ABCD is a parallelogram. So because it's a parallelogram, opposite sides are equal. Because it is cyclic, opposite angles are supplementary. Here I've done with A and C. Let's do B and D. Okay. Now because it is cyclic, anything you can use first, children. Okay, because it is cyclic, opposite angles are supplementary. Angle B is equal, angle B plus angle D is 180. Because it's cyclic, opposite angles are supplementary. But it's also a parallelogram. So opposite angles are equal. Angle B is equal to angle D. That means angle B plus B, because D and B are equal. So B plus B is 180. Twice of angle B is 180. So angle B is equal to 90. Now what's the definition of a rectangle? A parallelogram in which one angle is a right angle. A parallelogram in which one angle is a right angle is a rectangle. ABCD is already given to be a parallelogram. And we have proved that one angle, that is angle B, is a right angle. Therefore, ABCD is a rectangle. It is cyclic, so opposite angles are supplementary. Angle A plus angle C is 180. And it's a parallelogram, so opposite angles are equal. Angle A is equal to angle C. So A plus C is 180, but A and C are equal. So A plus A is 180. So like this, we get angle A is 90. ABCD is already a parallelogram. And now we have proved that one angle is a right angle. So it's a rectangle. Yeah. ABC and ADC are two right triangles with common hypotenuse AC. The diagram is incorrect in case 2. Sorry. Yeah, sorry, children, because of my bad throat, I'm just going on mute every now and then. Yeah. So here, no, I was telling you that the diagram in case 2, by mistake, I put the same thing. I have to change this. So let me not use the slide and talk. We'll do it here. ABC and ADC are two right triangles with common hypotenuse AC. ABC and ADC are two right triangles with common hypotenuse AC. Prove that CAD is equal to CBD. Now we don't understand. We have to draw the diagram to understand what we have to prove. So you can see that the common side is AC. AC, common hypotenuse AC. So now the cases can be like this. Right triangle. Right triangle. Okay. AC, ABC, ADC. So here in this case, the what is this B and D? That is the two triangles. They lie on either sides of the hypotenuse. In this figure, the two triangles ABC and ADC, they lie on either sides of the hypotenuse. They can also have a situation like this. The two triangles on the same side of the hypotenuse. ABC, ADC. Okay, now this is 90. Okay, let me draw it better. 1 second. Yeah. Yeah. So ABC and ADC. In figure 1, the two triangles lie on either sides or on the opposite sides of the common hypotenuse AC. In figure 2, the two triangles, they lie on the same side. The same side can be above or below. It's same side can be above or below, both above or both below. You don't have to take that as another situation. That is above as one and below as another. Okay. Okay. So this one is given. Two right triangles with a common hypotenuse AC. So AC is the common hypotenuse. Prove that CAD, this angle is equal to CBD, this angle. CAD is equal to CBD, this angle. Now in this figure, CAD, CBD, CBD. We'll see the figures again. The proof is very simple. So see here, we can take two cases. The two right triangles lying on the same side of the hypotenuse AC, or the two triangles lying on opposite sides of the hypotenuse AC. Anything can be taken as a first case. So all right. So we'll finish this case and then take up the next one. So this is the case where the two triangles, they lie on the same side of the hypotenuse of the common hypotenuse AC. Both of them are right triangles, which is why we have angle B is 90 and D is 90, because AC is the hypotenuse. And we know that the angle opposite of the hypotenuse is the right angle. The angle opposite of the hypotenuse, AC. So angle B, angle D are right angles. Now we need to prove that CAD is equal to CBD. All right. Now before that, before we mark angles CAD and CBD, now here the points A, B, D, and C. The points A, B, D, and C are concyclic. Why? Because the first session on circles, we understood that if a line segment joining 2 points, I'll share the recordings, I'll share the playlist, maybe you can watch it again. If a line segment joining 2 points subtends equal angles at 2 other points lying on the same side of it, then the 4 points are said to be concyclic. We saw this theorem in the first session of circles. So you can see here, if a line segment joining 2 points, so A and C are the 2 points, and AC is the line segment joining the 2 points. If a line segment joining 2 points subtends equal angles at 2 other points lying on the same side of it. So B and D are the 2 other points lying on the same side of AC. And AC makes equal angles at B and D because both is equal to 90 degrees. Okay, so since angle B, angle D both equal to 90 degrees, the line segment AC subtends equal angles at the points B and D lying on the same side of it. If all this is happening, then the result is the 4 points are concyclic. The points A, B, D, and C are concyclic. I repeat, if a line segment joining 2 points, A and C are the 2 points, and AC is the line segment joining the 2 points. If the line segment joining the 2 points subtends equal angles, yeah, the angles are equal because 90-90, subtends equal angles at 2 other points. The 2 other points are B and D. And the 2 other points should lie on the same side of it, same side of the line segment. Yes, B and D lie on the same side, both lie above AC. So if the line segment joining 2 points subtends equal angles at 2 other points lying on the same side of it. So AC subtends 90 degrees at B, AC subtends 90 degrees at D. So AC is making equal angles at B and D. In this situation, the 4 points A, B, D, and C are concyclic. That's what we can conclude by the theorem. The points A, B, D, and C are concyclic. There should be a line segment joining 2 points. There should be 2 other points lying on the same side of the line segment, either above or below. And this line segment should make equal angles at those 2 other points. And yes, it is making, AC is making equal angles at B and D, 90-90. If all this is happening, then the result is, by the theorem, the points A, B, D, and C, the 4 points, are concyclic. So that means you can draw a circle passing through these 4 points. Now what I draw may not look like a circle, but there is a circle that can be drawn passing through these 4 points. Now let us understand CAD and CBD. So now CAD and CBD clearly are made by the same arc CD at the points A and B on the circumference. The arc CD, CAD, CBD. From the name, we can make out CAD, CBD. CD is the arc. CD is the arc. So arc CD makes angle CAD at A and CBD at B. So the theorem is angles in the same segment of a circle are equal. Angle CAD is equal to angle CBD because angles in the same segment of a circle are equal. The arc is here. CAD. CAD. CBD. CBD. These two angles are equal because they are in the same segment. You can see this is the chord. This is the arc. This is the chord. This is one segment. And that's the other segment. So angles in the same segment of a circle are equal. Therefore, CAD is equal to CBD. CD is the arc that makes angles CAD and CBD at the points A and B on the circumference of the major segment. So this is case 1. Case 2 is when the two triangles lie on the opposite sides of the common hypotenuse AC. Yeah. ABC, ADC. AC is the common hypotenuse. So this is the other case where the two triangles lie on either sides, opposite sides of the common hypotenuse AC. So here directly the quadrilateral ABCD is concyclic because you can see that one pair of opposite angles are supplementary. Angle B plus angle D is equal to 180. See, in both the cases, in the case which we already discussed and in this case, in both the cases, you'll have to prove that the 4 points are concyclic. You'll have to prove that the 4 points are concyclic because this result CAD is equal to CBD is proved using the theorem that angles in the same segment of a circle are equal. CAD, CBD, CD is the arc, no? So you can prove this result using the theorem angles in the same segment of a circle are equal. So from where will we get a circle? In the question, there is no circle. Then from where will you get a circle? You get a circle only when you prove that the points A, B, C, and D are concyclic. That's why in both the cases, we prove that the points are concyclic. So we know that there is a circle passing through the 4 vertices. And then we use the theorem. Angles in the same segment of a circle are equal to prove that angle CAD is equal to angle CBD. So here, I must watch this recording. I know it's going to be very funny. Yeah. Yeah, children. So here you see that angle B plus angle D is equal to 180. 90 plus 90, 180. So in the quadrilateral ABCD, one pair of opposite angles are supplementary. Therefore, ABCD is a cyclic quadrilateral. Therefore, there is a circle passing through the 4 vertices. Now CAD, this angle, CBD, you'll have to join this. So now CAD is equal to CBD because angles in the same segment of a circle are equal. Both the angles are made by the arc CD at the points A and B on the circumference. Angles in the same segment of a circle are equal. Am I clear, children?
Yes, ma'am.
Yes, ma'am.
Okay. Okay. Now, this arc AP in this figure, this arc AP, it makes ABP on the circumference. Can we see that? ABP, this angle, this arc, the arc AP, the arc AP makes angle ABP on the circumference. The same arc AP makes ACP. ACP. So angle 1 is equal to angle 2. Angles in the same segment of a circle are equal. ABP, ACP. ABP, ACP. Made by the same arc AP at the points B and C on the circumference of the first circle. Actually, B and C are the points of intersection. So they lie on both the circles. Because in the figure, you see two intersecting circles, and B and C are the points of intersection. Abhishek, you want to say something? The two circles are intersecting circles. Disable your mic, Abhishek. Okay. In the first circle, the two circles are intersecting circles. The points of intersection are B and C. In the first circle, consider the arc AP. AP makes ABP, ACP on the circumference of the first circle, which are marked as angle 1 and angle 2. Angle 1 is equal to angle 2. Angles in the same segment of a circle are equal. Consider the arc DQ in the second circle. Consider the arc DQ in the second circle. Take the same points, B and C on the circumference. D, BQ, D, CQ. DBQ, DCQ. This angle, this angle. Sorry. So angle 3, angle 4. Angle 3 is equal to angle 4. Same theorem. Angles in the same segment of a circle are equal. The angles are made by the arc DQ at B and C. DBQ, DBQ, which is angle 3, and DCQ, which is angle 4. So DBQ is equal to DCQ because both the angles are made by the same arc DQ at the points B and C on the circumference. Angles in the same segment of a circle are equal. So we have these results. We have angle 1 equal to angle 2. We also have angle 3 equals angle 4. And we also have angle 1 equals angle 3. We have 1 equals 2. 3 equals 4 and 1 equals 3 because vertically opposite angles are equal. 1 is equal to 3. So yeah, this one we proved. Angle 1 is equal. 2 and 4 are not vertically opposite. 1 and 3. 1 and 3 are vertically opposite angles. So when you compare all these results, because 1 is equal to 3, that means 2 is equal to 4. 2 is equal to 4. What is 2? This is only angle 2. And is equal to 4. This is only angle 4. Hence proved. That's what we have to prove. We have to prove that ACP, which is angle 2, is equal to QCD, which is angle 4. So in the first circle, angle 1 is equal to angle 2. Angles in the same segment of a circle are equal. In the second circle, angle 3 is equal to angle 4. Angles in the same segment of a circle are equal. With this, we also have angle 1 equals angle 3, vertically opposite angles. So since angle 1 equals angle 3, it means angle 2 is equal to angle 4. And that's what we had to prove. 2 equals 4. ACP is angle 2, QCD is angle 4. This one will be easy to understand because we've seen a similar one in quadrilaterals. I think the last proof in quadrilaterals. Yeah. So if the non-parallel sides of a trapezium are equal, prove that it's cyclic. Meaning as an isosceles trapezium. An isosceles trapezium is cyclic. An isosceles trapezium is cyclic. Children, I'll take another 15 minutes because I just have something more to finish. So children who are, who have to leave the meeting for some reason can leave the meeting. I'll share the recording. You can make use of the recording. Yeah. So another 10 minutes, I think by 9:45 to 9:50, we'll wind up today's session. All right. So the statement is, if the non-parallel sides of a trapezium are equal, non-parallel sides equal meaning it is an isosceles trapezium. So the statement is prove that an isosceles trapezium is cyclic. So how will you prove that it's cyclic? You must prove that one pair of opposite angles is supplementary. One pair of opposite angles is supplementary. So draw a trapezium. It's an isosceles trapezium. Non-parallel sides are equal. AD is equal to BC. Construction, we have seen this earlier. Draw perpendiculars AM and BN on DC. Show that these two triangles are congruent. So we have right angle by construction. Hypotenuse AD equals hypotenuse BC because it's given. And AM is equal to BN because the perpendicular distance between two parallel lines is the same everywhere. Because AB and CD are parallel lines, the distance between two parallel lines is the same everywhere. So AM is equal to BN. RHS rule, the triangles are congruent. CPCT, you have this angle is equal Yeah. So yeah, we have to prove that these two triangles are congruent. CPCT, this angle equals this angle. So that's, we'll have that. Now, this angle plus this angle is 180. Why? Because co-interior angles are supplementary. Parallel line, transversal, parallel line. Co-interior angles are supplementary. So angle 1 plus angle 2 is equal to 180. Co-interior angles are supplementary. Angle 1 plus 2 is 180. But sorry, let me not use 1 and 2. You'll get confused. Sorry. Let me mark this as 3, 4, and 5. Okay. We have proved that angle 3 is equal to angle 4 through congruency. 3 is equal to 4. Now, 3 plus 5 is equal to 180 because co-interior angles are supplementary. Now, we have proved that 3 is equal to 4, right? So we can replace 3 with 4. So what's the result you have? 4 plus 5 is 180. Opposite angles are supplementary. Therefore, ABCD is cyclic. So take up these two triangles, show that they are congruent. CPCT, angle 3 is equal to angle 4. Angle 3 is equal to angle 4, CPCT. Now, angle 3 plus angle 5 is 180 because co-interior angles are supplementary. Parallel line, transversal, parallel line. 3 and 5 are co-interior angles, they are supplementary. So 3 plus 5 is 180. But we proved that 3 is equal to 4, right? 4 plus 5 is equal to 180. And what does that mean? 4 plus 5 is 180. Opposite angles, 4 and 5, they're supplementary. So in ABCD, one pair of opposite angles are supplementary. Therefore, ABCD is cyclic. If the diagonals of a cyclic quadrilateral are diameters of the circle passing through the vertices of the quadrilateral, prove that it is a rectangle. If the diagonals of a cyclic quadrilateral, so the quadrilateral, see, we need to finally prove it's a rectangle, children. That's why you see that ABCD already looks like a rectangle in the figure. If the diagonals of a cyclic quadrilateral, so the diagonals are AC and BD, the diagonals are diameters. So AC and BD are diameters and diameters of the circle through the vertices of the quadrilateral. Yeah. So ABCD. So ABCD is a cyclic quadrilateral. The diagonals of the quadrilateral are diameters of the circle. In this situation, we need to show that ABCD is a rectangle. What is given? ABCD is a quadrilateral. It's a cyclic quadrilateral. ABCD is a cyclic quadrilateral. Now, quadrilateral, there are two diagonals. AC and BD are the two diagonals. Now, these diagonals are the diagonals of the quadrilateral, of the cyclic quadrilateral, are diameters of the circle. Is given. AC and BD are diagonals for the quadrilateral and diameters of the circle. If this is given to us, we need to prove that ABCD is a rectangle. Now, from where should we travel? We should come from quadrilateral to rectangle. We have a cyclic quadrilateral. From there, we should come to a rectangle. So we need to prove that the cyclic quadrilateral is a parallelogram first. And in the parallelogram, one angle is a right angle. So it is a rectangle. That's the definition of a rectangle. A parallelogram in which one angle is a right angle is a rectangle. So the given is a quadrilateral. We have to prove it's a rectangle. So first show that it's a parallelogram. And then in the parallelogram, prove that one angle is a right angle. And so it is a rectangle. Now, O is the midpoint of both AC and BD. Because AC and BD are diameters. AC and BD are diameters. Sorry. Because AC and BD are diameters, O is the midpoint, right? The center of the circle will be the midpoint of the diagonals. So O is the look at AC and BD as not diagonals, diameters. They are diagonals, but look at them as diameters. AC, diameter of the circle. Therefore, O is the midpoint of AC. BD, diameter of the circle. O is the midpoint of BD. Diameter, no? So O is the midpoint. That means what? O is the midpoint of both AC and BD. Now treat them as diagonals. So for both the diagonals AC and BD, O is the midpoint. That means the diagonals bisect each other. Then ABCD is a parallelogram. How do you prove that quadrilateral is a parallelogram? One of the criteria is if the diagonals bisect each other. One of the criteria is if the diagonals bisect each other, it's a parallelogram. And how do you show that the diagonals bisect each other? Both the diagonals should have the same midpoint. For that, we need to first treat the diagonals as diameters. AC diameter, O midpoint. BD diameter, O midpoint. So O is the midpoint of both AC and BD. Now look at them as diagonals of the quadrilateral. Both the diagonals have the same midpoint O. That means the diagonals bisect each other. If the diagonals of a quadrilateral bisect each other, then the quadrilateral is a parallelogram. So like this, we prove it's a parallelogram. Now in the parallelogram, if one angle is a right angle, it's a rectangle. Now because this is the diameter, angle in a semicircle is a right angle. This one is 90 degrees. Or you can use this one also. You can see like angle in a semicircle is a right angle. See, in fact, you can prove all the four are 90 degrees, children. See here. This is the diagonal, no? This is the diameter, right? Diameter. So pull the ends of the diameter to this point D. So this is 90 degrees. You using AC as the diameter, you can show that this is 90 and this is 90. AC is the diameter. Join A to B, C to B. This is 90. If you treat BD as the diameter, B and D are the endpoints. Join D to A, B to A, 90 degrees. Again, BD as the diameter. C is the point on the circumference. Join B to C, D to C. This is 90 degrees. You write any one, that's enough. Reason angle in a semicircle is a right angle. So in the parallelogram, one angle is a right angle, so it's a rectangle. Or you can also do this. You can prove that every corner is a right angle. Yes, sorry. So you can prove that every corner is a right angle. You can prove that every corner is a right angle using the theorem angle in a semicircle is a right angle. Once you do prove this, every corner is a right angle. Use this criteria to show that a quadrilateral is a parallelogram. If both the pairs of opposite angles are equal, then the quadrilateral is a parallelogram. If both the pairs of opposite angles are equal, then the quadrilateral is a parallelogram. So since both the pairs of opposite angles are equal, ABCD is a parallelogram. And also in the parallelogram, every angle is 90, but for the sake of the definition, you can mention one angle A is 90, therefore ABCD is a rectangle. You can also do it like that. So the proof which you see on the slide, what I've written is the diagonals bisect each other, so it's a parallelogram. And then using the theorem, angle in a semicircle is a right angle. One angle is equal to 90 degrees. Therefore, in the parallelogram, when one angle is a right angle, it's a rectangle. A chord of a circle is equal to the radius of the circle. A chord of a circle is equal to the radius of the circle. AB is a chord only. AB is not radius. But suppose, so now OA and OB are the radii, right? So R. AB is also R, meaning the length of AB is R units. AB is not the radius. AB is chord only. But it's the length of the chord is equal to the radius. The length of the chord. So supposing 5 centimeters. So a chord of a circle is equal to the radius of the circle. If the radius is 5, the length of the chord AB is also 5. So that means the triangle is equilateral. The triangle is equilateral. All the sides are equal. So each angle is 60 degrees. Chord equal to the radius. So OAB is equilateral. I'm just taking for example 5. It's not given 5. It's not 5. The length of the chord is equal to the radius of the circle. So that means all the three sides are equal. So the triangle is equilateral, meaning this angle is 60 degrees. Each angle is 60 degrees. Find the angle subtended by the chord at a point on the major arc and also at a point on the, find the angle subtended by the chord at a point on the minor arc and also at a point on the major arc. Okay, so this one is the minor arc. This one is the minor arc. Now let's take this point C on the minor arc. Now this is now join the ends of the chord to this point C. C is a point on the minor arc AB. Join the ends of the arc to this point C. So you need to find the measure of this angle. Take another point D on the major arc Join A to D and B to D. You must also find the measure of this angle. You must find the measure of this angle and this angle. So if this is 60, this angle will be 30 because angle subtended by an arc at the center is double the angle subtended by it at any point on the remaining part of the circle. Center is always double. So if this 60, this 30. Then cyclic quadrilateral, opposite angles are supplementary. So there will be 150. Circle, chord, center, radii, equal, equilateral, 60, point on the minor arc. A and B are the ends of the chord. Join A to C, B to C. This is the angle subtended by chord AB at the point C on the minor arc. Take another point D on the major arc. Ends of the chord A and B. Join A to D, B to D. This is the angle subtended by the chord AB at the point D on the major arc. We need to find the measure of this angle and this angle. This angle is equal to 30 degrees because this is 60. AOB, ADB. AOB, center, 60 degrees. ADB, circumference, 30 degrees. Now, ADBC is cyclic. Opposite angles are supplementary. So this is 30, no? So this should be 150. This angle is 150. Yeah, okay. The rest are numerical. Yeah. We'll understand this one and wind up the session for today, children. Prove that the quadrilateral formed by the internal angle bisectors of any quadrilateral is cyclic. Prove that the quadrilateral formed by the internal angle bisectors of any quadrilateral is cyclic. So you can see a quadrilateral ABCD. Quadrilateral ABCD, it's any quadrilateral. These are the bisectors. AP is the bisector of angle A. BP is the bisector of angle B. CR is the bisector of angle C. DR is the bisector of angle D. You need to prove that this quadrilateral PQRS, this one, is cyclic. Any quadrilateral ABCD. These are the four internal or interior angles. Bisector of A and B. They meet here. Say bisector of C and D. Bisectors. So so we have shown the bisectors of the four angles, interior angles A, B, C, and D. Now they form a quadrilateral here. You need to prove that this quadrilateral is cyclic. So how do we prove that this quadrilateral is cyclic? The only property we know is you should prove that one pair of opposite angles is supplementary. Then it is cyclic. Remember that these are the bisectors. This angle is bisected now. Angle A is bisected. So this one is equal to this one. Angle B is bisected. C is bisected. D is bisected. All right. So what we're going to do is we're going to find this angle and this angle very easily using angle sum property. Very easily using angle sum property. We'll find the measure of this angle and this angle, children. Why these two angles? Because angle P and angle R, they're the opposite angles of PQRS. Angle P and angle P and angle R are opposite angles of PQRS. So if you prove that P plus R is 180, if you prove that P plus R is 180, then PQRS is cyclic. You can also prove S plus Q. You can also do this. Any one pair. Okay, this one, see, I've chosen P and R because you can directly find, if you take up this triangle PAB, no, you can directly find angle P. If you take this triangle, you can directly find angle R. If you want to prove this angle plus this angle is 180, you can do it. You should find this angle from this triangle. And then you must say vertically opposite angles are equal and write for this. Similarly, you should find this angle of this triangle and then say vertically opposite angles are equal and write this angle and show that the sum is 180. So you can do that. But when you take up this triangle, no, directly you will get this angle. And when you take up this triangle, this angle. So how do you find this angle? Very easy. This one is half of angle A. This one is half of angle B because it's bisected. So this angle P will be 180 degrees minus half angle A minus half angle B. Directly angle sum property of a triangle. In triangle, in triangle APB, okay, this angle is equal to 180 degrees minus half of angle A minus half angle B. In the same way, in this triangle, angle R, which is angle DRC. Okay, this angle. In this triangle, these are the three angles. These are the three angles. This is half of angle C because it's bisected, half of angle D, bisected. So this angle R is 180 degrees minus half angle C minus half angle D. Simply angle sum property, children, in the two triangles. So now add these two angles because we found angle P and angle R. No, now add these two because we want to prove that P plus R is 180. So add the two results, APB plus DRC. See, this is nothing but angle P. This is nothing but angle R. Add the two results. So angle APB plus angle DRC is equal to 180 and 180 is 360 and minus half angle A minus half angle B minus half angle C minus half angle D. Adding the two results. Now take out minus half common and in the bracket you will get angle A plus angle B plus angle C plus angle D. Take out minus half common. So minus into plus minus, minus into plus minus. It will be plus in the bracket, not minus. Angle A plus angle B plus angle C plus angle D. Now that we know is 360. Angle sum property of a quadrilateral. Angle A plus angle B plus angle C plus angle D is 360. So half of 360 is 180. So 360 minus 180 is 180. So we have proved that in the quadrilateral, this angle plus this angle is 180. So in the quadrilateral PQRS, angle P plus angle R is 180. Therefore, PQRS is cyclic. All right. All right, children. So just give me some time, not today. I'll try to share the images by tomorrow. I'll also share the recordings of this chapter. So you can make use of the holidays to revise the chapter and also complete all that we have understood in today's session. All right. Children, use emoji, raise your hand. Okay, very good. Thank you, Abhishek, Kamalika, Niveda, Mritsa, Prenu, Anirudhan, Bhavishya, Haripranav, and Sahana. I hope Sahana's there. All right, children. So that's it for today's session. Thank you so much. Good night. You may leave the call.
Thank you, ma'am.
Thank you, children. Thank you, children. Good night.
Thank you, ma'am.
Thank you.